Yeah, importantly, I would like to thank the organizing committee for the opportunity. It was indeed a pleasure to be part of such an esteemed conference. The paper I submitted, or that was applying machine learning analysis for software quality test, it's intended specifically to look into the issues whereby we are having software development which is on a vast scale, specifically like the corporate houses which are in software development. I'll further talk on this in the conclusion as to what could or might be the limitations of the approach or the test that we have applied. Basically, a software release may be public or private and generally signifies the unveiling of a new or upgraded version of the application. So in software development, the release is deployable software package. That's what it is like, and mostly it is by the big software houses. And in several iterations, it can be made before the end of another iteration to follow. Obviously, that means it's going to be like in release form, 1 version, 2 version, 3 version, whatever. Residual defects is one of the most important factors that allow one to decide if a piece of software is ready to be released. So in theory, we can find all the defects and count them. However, it is impossible to find all the defects within a reasonable amount of time. This can be due to the variety of errors that exist or may exist in the software development or in the process of analyzing the release. Can a technique to forecast the software residual defectiveness using machine learning can be looked into as a solution to the challenge of predicting residual flaws? This is what the paper or the article proposes to be. So this, having said the overview, we go to the background review of some of the aspects which are related to the machine learning in software analysis, fault diagnosis. One of the common, or the oldest that we do find is the Maccabi complexity measure, which assesses independent program flow pathways, quantified programs complexity, different change metrics, including revisions, bug fixes, etc., etc. So this is one of the more traditional approach and one of the earliest approach. And then we have the analysis revealed that random forests were frequently the most effective models. This is one of the survey that we found out that, in the machine learning algorithm, random forest for software quality assurance has been one of the most effective. Then we have regressive approaches can be created on either lines of code or complexity, but after that, Bayesian belief networks for predicting failures have to be applied. Now, the research questions, we made 2 research questions in this article. One, to predict the failures in software using ML. And the second is how the clusters of software features can be created using machine learning to aid in failure prediction. We move on to question number 1. Before that, the methodology that applies was to apply or have the data set. And the data set that we applied was made up of 4 subsets, namely trouble reports, software feature data, commit data, and miscellaneous information. So the trouble reports were the information on the date, version, severity of the failure, and other info. Software quality feature was includes high-level details about the feature, the date it was finished, and the period of development. Commit data is a description of each commit made to main branch, number of lines, code added, removed, changed, edited, and then the miscellaneous information like time, date, department, etc. So when we analyzed the research question 1, the following models or following ML model techniques were applied: LSTM, lasso, random forest, and support vector. And when we look or we analyze the models, the performance of the models, it was analyzed that the LSTM and the random forest were good results with categorical models, whereas lasso algorithm performed the best overall throughout the test when measured with all the data functions to minimize errors like hyperbolic tangent, R2, RALU, and on scalar data. Now, the difference here is that the categorical models are in general specifically a certain class of models, but on a scalar data, that is to be on the, you may say on a generally overall on any category of the data, the lasso algorithm was found to be performing better in fault analysis. Then test question number 2, research question number 2, from the clustering software. Now here we have the clusters which were identified and were analyzed using a DB scan and k-means. And again, the number of files were still larger for the lines of code, again, were analyzed in accordance to the k-means and DB scan on the basis of minimax, robust, quantile, and quantile normal, and quantile uniform. And the results from the clustering features on the subsystem level were again further analyzed on the same using the k-means and DB scans. Here we can see that the values that were received, we can see that the DB scans had a better prevailing measuring values as compared to k-means. So they were both tested and contrasted. And the table 7 provides, on the paper, we have a table 7 that provides the results of this at the systems level, where table 8 lists the results at the subsystem level. So depending on the preprocessor, DB scan can identify noise antlers, which make up between 5 and 15% of the data at the system level. Thus, it was concluded that a DB scan algorithm clusters may be more suited than the k-means ones for this reason. So in conclusion, if we see the conclusion, we have the error identification that were made. I'm sorry, this table is losing some data fields. Like there should be regression, random forest, support vector, LSTM, all should have been written in this table. But I think during the making of the presentation, the values or the headers have been misplaced. But this is table 14 from the paper, and it shows the comparison between all the machine learning algorithms that were used to look into the errors, MAE, MSA, R2, and F1 and F2. And it was further concluded that LSTM on all test sets become the top algorithm overall. We know that lasso performed good in test number 1, but in test number 2 and in test number 1, again, the LSTM approach was more fundamentally prevailing. So if we are not using, or if we are not going to use a clustering approach, then yes, lasso can be is identified for, a lasso approach can be good for fault diagnosis. But if we have clusters whereby we have a lot of different data segments or different data which are going to be created into cluster, and then we have to fault diagnose for that, then LSTM approach gives the better results. Now, some of the limitations for this approach is that the version or the data or software that is to be released has to be of an extensive number of lines of codes. It's not to be meant on smaller versions, and it cannot be on a small programs. So the approach has to be applied on extensively large amount of program that has lines of codes. We were able to have this data from a private company that has about, for the 4 years of their software development, the programs and the lines of codes and the cluster that they had gathered over the period of time. So we are thankful to them. Unfortunately, I was not allowed or told to name the company, but we gather the data from a private company for that. So this is the paper that was submitted. Thank you.
Thank you very much. I have a few questions. The first one is, let me understand it clearly. So you are predicting the amount of defects and the bugs in the software, which we don't know now, but we expect to know this number using the machine learning approach. So it's
yes, sir.
Non-deterministic. And how do you validate that? How do you know that your prediction is actually accurate?
There's something we call optimization. One of the approach of looking into how well your lines of code or program perform is by optimization. And this is what we have done. by looking into the effectiveness of the program, how effectively we can reduce the lines of codes, that is where the actual error lies. If the program is being compiled still, after that reduction, we know that we have, number one, we have successfully optimized the lines of codes. And then obviously anything that goes or after is made after that optimization, it can be predicted that a certain error will occur because that has a bug. And different bugs are classified during optimization. That can be, on basis of those bugs, you can predict that certain error is more likely to be, creating a fault in the software in the future.
And what is the accuracy or precision of your predictions? Do you have some numbers?
That I don't have. That the accuracy, it's very difficult to calculate actually the accuracy of how much we can, let's say the lasso algorithm will effectively find the bug. It goes anything. I mean, we were successful almost in all the data sets where we were used. I wouldn't say 100%, but at least it was more than 90% for any standard release that was on which we worked. But the problem with accuracy, we are not here more concerned with the accuracy. We are more concerned with predicting the failure. So if the failure exists there, it will be identified. Now, the accuracy can be based on many other factors. It doesn't have to be machine learning. It can be design error. There can be design methodologies that can be one of the reasons. What kind of software development model we are using, that can also be can cause a difference in accuracy levels. Yeah.
And did you put this instrument or the method into production? Because you mentioned the company.
No. Again, more of the companies, we had a talk with the company. Actually, one of the problems is that the approach is not standardized. For any approach to be incorporated on a large scale, it has to be standardized. So let's just say it is not standardized. I mean, you rightly mentioned the accuracy. In standardization, we have to have the accuracy levels, but which we don't have. But
it seems like you're making the first step into the long process.
Exactly. This is like an attempt, and to proceed further, hopefully, maybe, get more analysis done on the accuracy level, maybe apply more neural network approach further in software development, etc. Now, this is where you see, this is where we can consider, like, now we have ChatGPT, like, let's say example. Now, how much of accuracy is ChatGPT giving us? We know it gives accurate, or it can be error. But like you mentioned, what is the accuracy level? So this is something we are going to look into. You have rightly pointed out that accuracy level. How are we going to judge the accuracy level? Because this is something is an issue in software development, especially when you are optimizing lines of code. So how are we going to look into the accuracy level of your optimization?
Yeah, that's basically, this metric is very well connected with the trust people give to the tool. So if the accuracy is high, or at least it's perceived as high, then people tend to trust the tool. So that's why I'm asking this question, because we also do some machine learning related projects, and people very often ask me in the end, what's the accuracy and the precision, and whether these metrics are measured with the people involved. So not only the machines, but actually, what do people think about the numbers you produce, about the predictions the machine produces? So that's why I'm asking.
True.
Yeah. All right, then thanks everybody. I think we finished for today. Thank you for coming. Thanks for considering our conference. I hope you come to us next year, because we definitely will continue. So we already starting announcing the next year conference. So please consider us. Thanks. It's officially closed. Bye-bye.
Bye. Thank you so much. Thank you, everyone.